very happy to have Mboro from who is going to tell us about the geometry of the cube.
Well, thank you for this opportunity to talk about, to give this talk. So my talk will revolve around the rationality question for cubic hypersurfaces. So I recall first some definition about rationality question. So if I take a complex manifold or variety of dimension, I can look for, so by definition, we know that X has I would say holomorphic charts, but we can look for, say, algebraic chart, meaning chart that would be given by rational function. So, and we, as in Zariski topology, the open set are big. Admitted such a chart, such a parameterization is already a strong property, which is not satisfied by every complex manifold. And those who satisfy this bear a special name. We say that X is unirational if there is a dominant rational map say, to X. So okay, and so as I said, you can think of this map being given by rational function. And there is a stronger notion than this one, which require the parameterization to be generically one-to-one. X is rational if there is a dominant rational map, like just previously. Now the dimension has to be the dimension of X, which is generically one-to-one. And then I don't think we will have time to talk about this last notion, but I introduce it anyhow. We say that X is stably rational if there is the X cross some projective space is rational. So there are obvious inclusion between the different families. So the strongest notion is rationality. So here we have rational varieties. Then we have stably rational variety. And then we have unirational varieties. And in dimension 1 and 2, all the three notions coincide. And starting from dimension 3, they stop coinciding. And the strictness of this inclusion was proven, for example, I think one of the first example was by Artin and Mumford with a special quartic double solid. And the strictness of this inclusion was proven by Beauville, Colotelen, Sansuk, and Sinerton Dyer, Swinen. And the example is free-fall fiber in so-called Le Châtelet surfaces anywhere. But those inclusions start to be strict. So in the case of hypersurfaces, which are some of the simplest example of algebraic variety. So,
what's the point that you're trying to make here? So they are the conclusion of the first and third one, but two are approximately at the same time, but Clement and Griffis and
yeah, I mean, so I'm talking about the successive inclusion. Of course, Clement and Griffis example and also Isconsit Manin prove that they were unirational, non-rational varieties. But I didn't put it because I didn't put a direct inclusion. I mean, to just.
I assume for still not known for three-dimensional distribution.
No, it is not known. I will.
So what about the quartic?
No, the very general one does not admit the composition of a diagonal by result of Collot-Telen and Al.
Because it can degenerate.
Yes, yeah. So they degenerate precisely to Artman-Ford. So if we look at the series of a simple series of examples, so for curves, as I said, they coincide, but the rationality is detected by a very simple thing, which is the genus. There is exactly one rational curve, which is P1, the Riemann sphere. For surface, I don't recall, but there is a Castelnuovo rationality criterion, which is just saying that if some tensor, I mean, it is a cohomological detected by cohomology of some bundle, and then if we go to more generally hypersurfaces, quadric are always rational, and then we move to the case of cubic. So let me, so in case of cubic hypersurfaces. So as I said, for not as I said, but for cubic of dimension 1, they are elliptic curves, so they are in particular non-rational, and for cubic of dimension at least 2, the claim is that there is a X admit an unirational parametrization of degree 2. Of degree 2. And how is it constructed? Just so I sketch the construction, pick a line inside the cubic, and look at the restriction of the tangent bundle of X to the line. So it gives a projective bundle, the fiber of dimension -1, and then when one can construct a rational map to X. So how? Just consider for a point and the tangent direction, one can associate the residual points in the. So a point and the tangent direction generate a line inside the projective space. I denote this line like this, and I can take the intersection of the line with X. Generically, it will not be contained in X, therefore the intersection will consist in 3 points. But since we have taken tangent direction, the intersection will contain the point X with multiplicity 2. And then therefore there will be just one residual point, and this is the point that we associate here. And to see that this map is generically 2 to 1, just if we are trying to analyze the fiber of one point, we can look at the plane generated by the line that we fixed here, and maybe I should have called it L naught, so that so this is a P2, and the intersection with X is a cubic curve which contains already the line L naught. So there is a residual conic And one can check that the preimage of P will be, so here, let me, okay, P, so this is the plane pi, this is P, this is L naught, and the preimages will be those two. Yeah. So, and then the situation for cubic hypersurfaces with respect to all those notions that I've presented at the beginning is the following. So unirational, stably rational, rational. So of course, for elliptic curve again, they are not rational. As I say, I've just proven, starting from dimension 2, they are all unirational. A cubic surface is always rational. It is a del Pezzo surface. And more precisely, it is isomorphic to the blow-up of P1 along at P2, sorry, 6 general points. And of course, as I said, all the three notions coincide when we are in dimension less or equal than 2. And in dimension 3, this is the cubic threefold is non-rational due to work of Clement and Griffis. A seminal paper, if there is. And we still don't know if there are stably rational cubic threefolds. We don't know nothing about stably rational cubic fourfolds. For rationality of cubic fourfold, we smooth, yes, smooth. I mean, everything is smooth. I'm not interested in singular. So for cubic fourfold, we know that there exists rational example of cubic fourfold, but the conjecture is that the very general one is not rational. But the conjecture is quite hard to prove. And for cubic fivefold, we have no information whatsoever. We don't have any example of rational ones or the non-rational ones. So a word on the tool that we will use to try to this problem. So we have the usual tool for variety. So we have homology, Betty homology. With the left shade package and odd theory. So that gives us sorry, polarized odd structure on the homology group of the cubic of so I mean by polarization, there is a bilinear form which is in even case symmetric and in odd case skew, and which has an Hermitian associated Hermitian form, which is of associated Hermitian form on the complex version of the homology, which admit odd decomposition. So there is an associated Hermitian form of this bilinear symmetric form, which is definite of given sign on the different part of the decomposition. Actually, I should put primitive to be more correct, but just to give the idea. So we have Betic homology, we have Char groups. First, for cubic hypersurfaces, of course, by Lefschetz theorems, hyperplane theorems, and also universal coefficient theorem. The homology group are torsion free, and also they are very simple. So they are 0 in odd degree unless the degree is equal to the dimension of the cubic. And the even one are equally simple. It is just Z generated by the restriction of the hyperplane class that I denote H, big H, unless, again, 2I is the dimension of the cubic. So the only interesting homology is the homology in the middle. This is just a reminder. And then we have Char groups or Char ring. So which can be thought of again as a kind of homology theory. So basically, so just to remind very quickly, we'll start with the free abelian group generated by subvariety of codimension of given codimension, for example, codimension D. And one divide by different kind of equivalence relation. For example, the rational equivalence relation is generated by things of the form, in this group of the form, let me call it like this. So, I just write and I explain. So they are generated by difference of members of family parameterized by P1. So this, when I look at the projection on P1, I require this projection to be surjective. Then I can think of the fibers of this map as member of the family parameterized by P1. And when I take the example, the difference of 2 points, then I mean the group of rationally trivial cycles is generated by those two. So and then I can form the proper Char groups, which are by definition it is the quotient of this free abelian group by this equivalence relation, and it can mean the sum of them can be endowed with the structure of a ring, commutative ring, by the intersection product. This is by work of Fulton and so on. People before. So is a commutative ring. So Char groups are usually much more mysterious than homology groups. And there are no, in general, no efficient way to compute them, but we can still try to scratch part of them using much nicely behaved homology groups. We have the cycle class. So this is just to remind cycle class map, which is a ring homomorphism. Well, I mean, when we take the direct sum, that goes from Char groups to homology groups, and we have so let me denote like this. So we can introduce the group of homologically trivial algebraic cycles as the kernel of that, and so here in general with the cycle class, we just have written a tiny part of the child groups. To go deeper into the child group and to analyze child groups that are homologically trivial, there is this tool introduced by Griffis, which generalized Abel-Jacobi map for curves. So it's called the Intermediate Jacobian, and it is complex torus constructed. Complex torus constructed using odd structure. The precise formula is something like this. So one take out half of the odd decomposition, and then divide by the lattice that we start with. And it comes with a map. Which is in some sense holomorphic or algebraic if the complex torus is algebraic. So holomorphic in the sense that if we have a family, let me call it C, family of codimension D cycles parameterized by a base B, then the map given by this from the base to the intermediate Jacobian, B associate phi C of B minus C B0, for example, if it was effective. So this will be homologically trivial, and then I use this map. So this map from a complex variety to another one is holomorphic. So those are the tools that we use that we will use to analyze the rationality of cubic hypersurfaces. But as we will see in this talk, it turns out that even the child group are not so useful to detect non-rationality, because it is what is expected actually of cubic hypersurfaces. So there are general, yes. It will take some time, but so let me try to recall. So you have a cycle. I don't know if I will be able to recall just on the something like this, which is trivial here. So it is you can write it as it is trivial here. So it is the boundary of something, and then you the right way to write. I mean, the easiest way is to rewrite this complex torus as something which has more to do with functionals. I mean, it's like in the case of curves also, you do that. You can I don't want to spend too much time on it, but it's like a bit like in the case of curves. You reinterpret those groups in order to let appear functional. I think I will be mistaken if I try to do this now. But it starts by writing this as a co-boundary, and then you do things. Yes, I was saying that yes, the Char group are not so useful to detect the non-rationality of cubic surfaces. So general result about Char groups quickly. By work of no, first unirationality of cubic. Unirationality gives us that the Char group of zero cycle is trivial, generated by a point. Just because when, I mean, if one has a pair of points here, lying in the open set, which is it by the unirational parameterization, one can consider pre-images, and then the pair of points will sit inside the, let me call it phi, the rational curve, which is the image of the line, for example, joining the two points. So this is a rational curve. And if you go to the definition of what is a rational equivalence, you will see that it says precisely that those 2 points are rationally equivalent. What again? Next,
sorry,
is Grothendieck-Lefschetz. Which
Can I
says
ask?
that the Picard group, which is the same as the group of codimension 1 cycle of X, is inherited from the Picard group of the projective space just by restriction. So it is just Z inherited by the hyperplane class. And then there is much more complicated Bloch-Srinivas, which uses K-theory and things like that, and that shows that because I mean, as the zero cycles are supported on the point, we have for cubic surfaces, hypersurfaces. I mean, we have okay. The algebraically trivial codimension 2 cycles that are the same as the homologically trivial, and they are the same as the point of the intermediate Jacobian. So already for dimension 3, it gives the description of all the Char groups, and the only interesting Char group is the Char group of 1 cycle, codimension 2 cycle, 1 cycle that sits by this those arguments in an exact sequence like this. So Z is the homology of X. So this is the cycle class. So it's just like the Char group of zero cycle of a curve. So it would not help us to tell the free fall from the that to say that the free fall is very different from the curve. Why the curve? Because if we are interested in proving rationality, a prototype of a rational free fall is the blow up of P3 in some curves and points, but points are not relevant. So when we do that, then features of curve shows up in the relevant feature of the blow up, and if the solid is rational, then he has some curve-like feature. So, and here as I explained, I said it is the case we see that the Char group doesn't, the Char groups don't help us. And what help us is the criteria. Yeah. So this is a cycle class. This homology group is cyclic, generated by the class of line, and the kernel are the 1 cycle homologically trivial. By Bloch-Srinivas, this is just Abel Jacobi. free. This is just as I described here. So it boils down to this complex torus. It's like in the case of curves, one has for curves. So this is the degree map, and the kernel is the peak zero of C or the Jacobian of C. That's why I say that it is a curve-like. Okay. So we have the Clement-Griffis criterion that was the thing that helped proving rationality, not only for cubic freefold, it helped to prove non-rationality, sorry, for many other freefolds. So it is the following. If Y is a rational freefold, then the intermediate Jacobian of Y. So what I failed to mention is that it is more than just complex. Those things are more than just complex tori, especially when one takes the primitive part. But in the case of hypersurface, there is no difference between the homology and the whole homology and the primitive part. They are polarized complex tori. The polarization comes from the polarization I talked about when I introduced homology. And in very nice cases, by work of Griffis, it will happen for cubic hypersurfaces. It will happen for cubic. For n equal 3 and 5. So D3 X with the polarization. D3 with the polarization and D5. So respectively, for cubic fivefold, will be R principally polarized abelian variety. In particular, they have a nice defined theta divisor, and so yes. So I come back to this criterion. It says that the polarized complex torus associated to Y has to be isomorphic to the Jacobian of a curve. To the Jacobian of a curve. As principally polarized abelian variety. The polarization is important in the theorem. And basically the crucial part the crucial thing that makes it work is that the Jacobian of a curve is irreducible as a principally polarized abelian variety. This is just because so the crucial part, the Jacobian of a curve is irreducible because the theta divisor is dominated by the symmetric product of the curve, basically. So it is irreducible because the symmetric product of the curve is. And then, so one use correspondence to show that the intermediate Jacobian of such thing will be a direct summand of the sum of Jacobian, and then by irreducibility it has to be a Jacobian, exactly. And then they use the geometry of the cubic, and especially the geometry of the variety of lines of a cubic to prove that it is not the case for cubic freefolds. I, I think I will skip the case of cubic fourfolds. It is more on the side of, I mean, the example given of rational cubic, I mean, the very interesting examples of rational cubic fourfold are given by Asset. I mean, he proved that there are a lot of them, and then many of the examples that are known to be rational are associated to a K-free. So there is a connection between the geometry of cubic fourfold and the geometry of hypercolor or K-free surfaces and things like that. But I will skip because I'm running out of time, and I will go to the case of cubic fivefold. So what kind of invariant can we cook out of the tool that we have introduced? So let me state, say, a proposition. If we assume we have, so we associate to each smooth projective variety, let me call it a group P, which is a subquotient. Let me say of char group of star codimension, a functorial subquotient. I mean, I want this to behave well under pullback and push forward. Yeah. Assume we have a series of those for each codimension, such that no. First, I assume we have given this association. Assume that there is n0 such that for any variety y and any k not exceeding n0, those subquotients vanish. Then, by blow-up formulas, so-called Manin formulas, P n plus 1 is a Rational invariant. So checking that something is a Rational invariant boils down in those nice case where we have those functionality to checking that it is invariant under blow-up. That's why I say by Manin formula here. And we have the same for such groups in char lower star, subquotient of char lower star, and the same thing for homology. For subquotient of a group of homology of except that for homology it will be +2. So an example we speak we make it a bit clearer. So let me take as an example the torsion in homology. We have that for any variety, this is torsion free because it is just a homomorphism from the pi1 to z. So in particular, it is torsion free. And of course, H0 is also torsion free, generated by the fundamental class. So what I see is that as a P, I can take the torsion inside the homology groups. So here we have seen that this is always 0 for star at most 1. Then by this thing that I have been telling, the torsion in H3, as I said, for homology, we have to take 2 degree more, is a Rational invariant. In this case, this is the so-called Artin-Mumford, I mean, the Gaussian invariant used by Artin-Mumford to prove the strictness of the inclusion that I talked about in the beginning. And it is also related to Mboro group and the generation of those, which is a series of invariants called unramified cohomology. So now I move to a much more interesting example for cubic. For cubic, of course, I mean, it's not interesting because the cohomology is torsion-free. Yeah. Yeah, so yes, I said it here, but I didn't write it. For cohomology, if it is a subquotient of a group of cohomology, it will be P. So the same thing, it will be Pn plus 2. That will be a Gaussian invariant. In Char group, it will be +1, and it will be +2. Sorry, I didn't write it. So something more interesting by work of, for us at least, by work of Bloch. Also, I can mention Collot-Hélène, Sansuc-Soulet. The kernel of the restriction of the Abel-Jacobi map from to the torsion cycles like this is 0 for any variety, for any x. So this is a kind of, so it says that the torsion classes in codimension group of codimension 2 inject in the Jacobian. This is also an analog to or generalization of Rothman theorem, but yeah, and also more classically, we know that the same happened for codimension 1 cycles, because codimension, I mean torsion and homologically trivial. Sorry. Because homologically trivial 1 cycle, so this is just a peak 0 of x, and the G1 is peak 0. So it is here we have an isomorphism. In particular, I mean, there is no kernel. So by our principle, it says that the group that I will denote like this the group of torsion classes that are annihilated by Abel-Jacobi is a Gaussian invariant. So, the same kernel of torsion. G5 is a Gaussian invariant. So I've tried to work on this computing or in or showing that this invariant vanish for cubic 5-fold, and the strategy was to go back to 1 cycle on the variety of line of the cubic. So the thing that I know f of x is the variety parameterizing lines on the cubic. But it didn't work out so nicely. So one first remark is that because x admit unirational parameterization of degree 2, all those kind of functorial invariant will be 2 torsion. So functorial directional invariant. R2 torsion. That vanish for projective space, of course, R2 torsion. I don't, those kind of thing that, for example, this one is 2 torsion. Okay. So one first result that is a refinement of a class. So you have the variety of line. Let me also introduce. So let P1 be the universal line above the variety of line. So it's, you can see it as a correspondence. So when it acts, we let it act, it yields a surjective morphism from one cycle of the variety of on the variety of line of the cubic fivefold. So n equals 5. To the codimension 3 cycle, which in this case are 2 cycles of the cubic surjective with z coefficient. So, but we don't quite understand the kernel of this correspondence in general. It is general complicated. Sorry?
Is there a conjecture or the kernel?
I don't think so. For example, even in the case of cubic threefold, the same thing will be true. Like there will be a surjective morphism from the zero cycle of the surface of a plane to the cubic, but the zero cycle on the surface of lines is already infinite dimensional because of this thing of Mumford and the zero cycle. So the kernel can be very nasty.
So when you say things that Mumford, so this is the fact that if you have a
holomorphic, yes, exactly. So we know that the Chow group on the cubic side is just as I said, is just extension of complex torus. But we know that so the thing that will be left in the kernel will be very big. I think will be the same here. So, but and here we would like to, instead of just have a lifting, to lift torsion classes, which is a much subtler problem. And so we would like to have more information on what kind of preimage you can take for a given class here. And this was done via an inversion formula. So, which idea again uses the geometry of the cubic. Let me. Now I think that you are more. There are more cases, but I don't remember the numbers. But at least there are more. I think probably starting from 5, it's okay. It works. I think it. No. Yes, starting from 5, it works.
Can be defined for any irrational variety parameterized between 2.
What do you mean? I mean, you're doing the I don't understand exactly. I mean so you can always, if you take a variety, for example, if the Picard group is cyclic, they would make sense to be interested in a curve of least degree that will play the role of line, and then you can try to do things and so. But here you really use the geometry of the cubic. It is done using osculating lines, which form osculating lines are lines such that the intersection of the cubic is just reduced to 1 point. And then those lines form a quadric bundle above the cubic, and then you have things of this. It is really use the geometry of the cubic. probably you can have similar results for other kinds of. So the inversion formula, so finding a nice pre-image is done. So I just sketch the idea. The idea is that if one starts with a subvarity inside the cubic, one can look at the residue map as usual. Taking, if we take 2 points, we can look at the residue inside the intersection of the line generated by the 2 points with x of x and y that we started from. There is one last point, and then this is what we take here. And it is not defined on the line that are contained in x. So, and then we can resolve this. Let me call them bisect for bisecant sigma. We have a resolution like that. And this can be seen as a correspondence between the two. And basically, the inversion formula will follow by computing the image by under this correspondence of the one of the very interesting divisor on this. Let me say that it is of dimension d, so it will be d, yeah. So where delta is the divisors associated to the exceptional divisor. So we have, so this is the Hilbert, sorry, yeah, denote this the Hilbert square. So the Hilbert scheme of length 2 subschemes. So there are either 2 distinct points or a point and a tangent direction. So, and this Hilbert square has a nice description as the quotient by the natural involution of the blow up of the diagonal. And delta is the class such that its pullback is exactly the exceptional divisor. It contains a lot of, as we can see from this, it contains a lot about the geometry of sigma, and so computing this image is very, I mean, can give very nice information. So basically, it's so and the result is that we get is that. But actually, it is not the way that the theorem is proven. This is just the idea. We get that for sigma subvarity, it doesn't have to be smooth. So let's say a surface, because we are interested in surfaces here. We have 2 degrees of sigma minus 2 sigma plus P1. So, I will introduce something which take into account that we have to blow up those points that are lying in line that are contained in X. So I will explain the notation. So this is the Plucker class. So this equality is in Chow, of course. P2 is the sits inside the Hilbert scheme of X. It is the space that parameterizes length 2 subscheme supported on the line of X. Subscheme supported X, and naturally it has a projection to the variety of lines. Just forgetful map that I did not P2. looking at the associative line, and this is just a P2 bundle. P2 seen as a symmetric product of P1 bundle. And I is just the inclusion here, IP. So basically this formula says that up to a cycle which is constant, I mean, it's not so interesting, it's just a restriction of the hyperplane, we can get the class of our surface as something which in which the interesting part is just the Hilbert scheme, the Hilbert square of the same thing. So the only, it says basically that the primate that you take is just the Hilbert square with some constant operation that you do, but it is basically the Hilbert square. And the very interesting part of this formula is, sorry, is that this coefficient is odd here. So it is interesting because, as I said, the cubic, because of the unirational parameterization of degree 2, the most of the birational invariant will be 2 torsion. And if it was because of the unirational parameterization of cubic of degree 2, most of the birational invariant will be 2 torsion because we take to projective space, it vanished and so on. And then if we add an even number, then we will not be able to tell anything about, I mean, you will not help us. But since it is odd, then we can work with 2 torsion things, and we are, it is. So, and with the help of this formula, and a little bit of more, a little more geometry, we can prove that the torsion lift. So we have this selectivity at the level of torsion classes. Torsion algebraic Jacobi on the cubic, on the Virchow line, subject to the group that we are interested in. So X torsion algebraic Jacobi. So for cubic 5-fold, everything is here for cubic 5-fold. Yes, but unfortunately, I was not able to work with curves on this variety, which is, by the way, Fano, to prove that this group vanished. But it was done later by Fu and Tian. So they proved that one has a sequence like this. So this is, again, it is a cycle, the cycle class. 6, 7, 10. So, and the way they do it is by using Bloch-August theory, which is something which is related to coniveau and ramified homology and Griffis groups and things like that. So they really go through the Bloch-August spectral sequence, and then showing one vanishing after the other, then they managed to prove this thing. So this tells us again that Char groups, because this is again something that looks like the presentation of the zero cycle on the curve. It tells us that Char group will not help us to determine whether the cubic is can be rational or not. So because this looks like the Char zero of a curve. So that there is no thing that tells you that it is very different from, and also in this case, we also have to rule out surface and freeform. Yes, yeah. Yes, it is also the Char groups that So the work of Clement and Griffis suggests that we have to dive more in the geometry of the intermediate Jacobian and use the different variety of line, variety of in this case plane, and so there are some work that are kind of ongoing. So there is a result of Colino that says that, so now if I consider not the variety of line, but the variety of planes contained inside the cubic, of the cubic fivefold, then I have the Abel-Jacobi induce an isomorphism of abelian variety. So this is the Abel-Jacobi for the planes. To five here. This is the Albanese of the so this is a surface dimension 2 of general type. Then we have an isomorphism here between those two abelian varieties. And then so some results that are not written but are easy to obtain is that it is easy to see that G5 cannot be the Jacobian of a curve. For X general. Of course, it doesn't help us because we don't have a Clement-Griffis criterion. But so the idea is that the degeneration, when we degenerate the cubic to cubic with one node, then the blow up of the node is isomorphic to the blow up of P5 . This map is the projection away from P0, the node, and the indeterminacy is resolved by blowing up the point. And what we find is that it is isomorphic to the blow up of P5 along the complete intersection of a cubic and the quadric in P5. And those varieties are non-rational in general. The general one is non-rational, and yes. So sorry, I don't remember every time that. Yeah. Okay. Yeah. Yes. Along a smooth intersection.
Here, because it's three-dimensional, as soon as it's moved, then it's operational.
Yes. So, and the way Beauville proved that it was not rational is by Clement-Griffis criterion, meaning that the Jacobian of this variety is not the Jacobian of a curve, and the G5 of the blow up is just isomorphic to this Jacobian with the polarization. G3 of this. So this is just by blow-up formulas. And then, so since the locus of Jacobian is closed inside the moduli space of abelian variety, principally polarized abelian variety, then it will tell us that this thing cannot be the Jacobian of a curve. So there is ongoing work on further property of the variety of planes and the intermediate Jacobian, but yeah, I think I'm over time.
So and just look at this blow up of P5 in the intersection of quadratic and cubic is very different host than the other
one. What we do is that because it is just nodal, there is a theory of Zucker and so it is right.
dimension of intermediate Jacobian of intersection of quadratic and cubic in people. 25. 20.
I don't know.
But wait, so once again, why is this not the Jacobian?
Probably, yeah, probably it is 21. Yeah, no, not probably. For sure, it has to be 21 because of the way that the thing is the argument works. It's like if one take the curve inside inside the space parameterizing cubic, for which some points are nodal cubic, represent nodal cubic, then one has a classifying map to the moduli space of principally polarized abelian variety of dimension 21. This is the dimension of cubic because those are smooth cubic, so it's just yeah. And because it is just nodal, there is a theory of work of Zucker, also a bit of Beauville. We can extend this map over the nodal, and what we find is that what we put to extend the map will be the intermediate Jacobian of the blow up of the nodes. So this so we can extend so that we have a map like this, and because those ones fall out of the locus of Jacobian, then the general will be not contained in the locus of Jacobian. Not if it is clear. So we have this map, let me call it phi, because phi of, say, P1 does not belong in the Jacobian locus. Let me denote it like this. Then the general one will not belong. So yes.
That's only proof that cannot be obtained by one P3 flow.
In a curve, yes, which is quite weak because we still have to deal with a blow up of surface and blow up of freefold, which is probably the main, the most difficult part. I mean, I've already over time, I think.
All right. One question. How much do we know about geometry of the final variety of lines or final variety?
In this, so what we know, so in the case of cubic fivefold, we know that the variety of line is Fano of index 1. We know, so of course the variety of planes now is a surface of general type. So as I said, we know that it's Albanese is isomorphic to the Albanese of a cubic. We know, so what do we know again? So we know, but this is ongoing. I would say that there are some calculations that need to be made. We know that there is a so-called tangent bundle exact sequence. So it's like an exact sequence describing the cotangent bundle of this surface. So it sits in exact sequence like this. So where those are the natural bundle on the Grassmannian. This is rank 3 quotient, and Q is the kernel. We have something like that. We know. So as I said, so this is okay without any more calculation, but it has not been published yet. But with more calculation to be done to check it. Sorry, for the statement about the surface of plane, we always take X to be general because in the case of variety of line, as soon as the cubic is smooth, the variety of line is smooth, but it is not the case for the surface of plane. Probably one can get by with deformation argument, but if the surface is not smooth, then it doesn't. There is no point in solving to have. So what is known again? So we have something like that. Something about the cohomological property, the property on the cohomology of the surface, which is quite natural. We know also, depending on this result, we know also the description of the Gauss map of this this surface of plane. I can write it quickly, but yes, it can be computed. So, but I don't know. So I just know the H1 and or H3. H1 is 2020. Say is H2. Sorry. Yes, H1 is 2020 is because we if only we know this isomorphism between Albanese and the intermediate Jacobian, and for H2, there are some big numbers that I don't have in mind, but it is computed. Or it can be computed. I don't know if there is some place where it is also computed, but it can be computed. It's not difficult. So,
meaning of the final services. Yeah, final variety of line.
Final variety of line is quite easy because there is a construction of, I think the first time it appeared was Galkin and Schindler.
I mean, if you know the Intermediate Jacobian, then by block Mboro is H1.
Yes, that's why I put 2020. But for H2, I don't have the number. But for the variety of line, it's easy because there is so we can all still look at this map of I mean residue map. So what we do is to look to keep the line also, to record the thing about the line. So instead of going to X simply, I go to X, but I also record the line that way. Yeah. And the thing is that, so it is not defined again on this P2 that I add, the length 2 subscheme supported on the line. And when you blow it up, you find out that it is isomorphic to, so this isomorphism to F1, isomorphic to the blow up of this thing. No, sorry. Along. Here you have inside of it P1, the correspondence of lines. So you blow up this thing, and you find that there is an isomorphism like that that identifies also the exceptional divisor. And using that, you can play with it is when you can find it, for example, in the note of Daniel Albrecht. You can play with you can rewrite this this thing as
You can find it where?
in the notes of Daniel Albrecht on cubic geometry of cubic hypersurfaces.
Yeah,
So
he likes to write. Okay.
yeah, so you can see this those isomorphism. So you can kind of write precisely what is involved in all of this in the Grothendieck ring of variety, and then you use some polynomials that involve all structure behave well with respect to that, so you cut and pass and so, and you can recover a lot of about the odd structure of this one.
All right, thank you.